So Ian is Group Engineering Manager at Ampcontrol and Chair of Standards Australia Technical Committee EL23 that oversees electrical equipment for mines and quarries. Ian studied at the University of Newcastle and has worked in academia and in industry, initially designing the inside of passenger trains and later as Innovation Manager here at Ampcontrol. More recently, in his role as Group Engineering Manager with Ampcontrol, he led the team in the development of and rapid prototyping of ventilators as part of the New South Wales response to the COVID-19 pandemic. He's been involved with Standards Australia since 2009 and with IEC Standards since 2015. So please welcome Ian.
Good afternoon all. So today we're going to talk a little bit about arc faults, perhaps, and also arc flashes, and think about this in the context of the hierarchy of controls. I do continue to be bemused from time to time at the detail we sometimes go to in various parts of electrical engineering without taking a step back and thinking about the whole. So I guess the presentation today is, if you like, an attempt to take a broader view of arc faults in electrical systems. My own background in this, I guess, comes about from a series of experiments we did at Ampcontrol a couple of years back, and the picture on the screen now is actually one of those experiments. We were trying to understand arc venting, and we have a saying here at Ampcontrol that Mother Nature never lies. And so if we have a theory, we'll do an experiment to try and prove it, and I think that's one of the most fun experiments I've ever got to do in my time at Ampcontrol. But we'll come back to that. So today, as I said, looking at arc faults and the management of arc faults, and it's designed to give non-experts an overview, if you will. There will be amongst the audience today many people who are experts in this subject area or in aspects of it, and I fully acknowledge those. So this, as I said, is a broader view. We consider both surface and underground applications, and by underground I don't necessarily mean just coal or tunnelling, but it's, I guess, in the context of a confined space. The picture you see there was another one of the experiments we did. So what is an arc fault? So generally it results from basically a short circuit through air, either from phase to ground or phase to phase. And they can be caused by many circumstances. If you have animals or foreign substances compromising clearance distances, accidental contact, poorly maintained equipment, build-up of conductive dust, work procedures, degradation of insulation, drop tools, lots of reasons why they come about. I have here a video that I'd like to show you, and I guess this was the closest I ever got, thankfully, to an arc fault. This was an experiment that was conducted down in Sydney at Lane Cove. All right, so what we've got here is an induced fault. It's 12.5 kA. Duration of the fault is 1 second. The enclosure is a stainless steel sheet metal enclosure. It's of the order of about 1 cubic metre. The orange square that you see is an arc vent, so it is designed to open up and allow pressure release from the enclosure. I'll run it on my screen here. And the overwhelming sense I get from that is you don't want to be near an arc flash or an arc explosion. It really is a huge ball of flame that comes out. It's very high temperatures, very high velocities, lots of molten metal in there, and it's to be avoided almost at any cost. So the arc faults are essentially an uncontrolled release of energy. You can pick a temperature as to what the plasma arcs may be. Typically, we hear numbers of around 10,000 degrees, sometimes say 20,000 degrees. I don't think it matters too much. It's way beyond anything sensible that we can manage. So not only do we have the very high temperatures, but we also have a potential ignition source for flammables, be they gases and or coal dust that might be in the vicinity. And of course, those high temperatures also give rise to radiation burns for anybody in the area. One of the other hazards that also comes around is the catastrophic failure of the enclosure itself. Because we have such high temperatures, the air inside the enclosure will expand rapidly. That increases the pressure in a finite volume. And of course, it's very rare for an enclosure to be designed to withstand that pressure rise. And so you get a catastrophic fail. Another means of failure is also burn through by an arc, where a sustained arc can actually just burn through the wall of the enclosure. Clearing a fault is non-trivial, so we generally reliant on being able to detect the fault, either through optics or heat or sound or overcurrent. Then we have to initiate some protection upstream of the fault and hope that that is activated successfully and also within a reasonable time frame. Here's a quote that I have attributed. I am unable to do the calculations myself to appreciate if it's accurate, but it is said that a face-to-face fault in a 480 volt system with 20 kA of fault current provides around 9.6 megawatts of power. If the fault lasts for 200 milliseconds, then the equivalent energy is something akin to half a kilogram of TNT. So whilst we might be able to sustain that in an installation out in the middle of nowhere, trying to contemplate that in a confined space underground generally doesn't bear thinking about. So what's the sequence of events in an arc fault? A couple of slides here are taken from some work done by Ken Byers and his team up in Simtars in the 1990s. And they did an enormous amount of work in trying to characterise arc faults, both in stainless steel enclosures and also in flame-proof enclosures. There's the report. It's available in the public domain if you want to go chase it. But what we see is the initial steep rise, which is almost linear, and that's after the striking of the arc. That is the heating of the air and the pressure rise inside the enclosure. So on the vertical axis, we've got pressure rise, and we have time on the horizontal axis. So the pressure starts to rise linearly. The sorts of numbers are 1 kPa per millisecond, or something of that order. If we have a vented enclosure, then once the vent is open, we basically allow the overpressure to escape, and so the pressure will fall. We note that on that picture there, the pressure actually goes negative, and that's because of the inertia of the air, and the cooling generates a vacuum inside the enclosure. The key bit is the vent actuation. So this is assuming you do have an arc vent fitted to your box, and of course it's critical that that vent actuation happens as soon as possible in time and at as low a pressure as is possible to protect the enclosure. So I showed you a couple of pictures earlier on of some experiments that we had done with some rooms, switch rooms. And there's results here for a 12.5 kA fault and a 20 kA fault. These were simulated faults. They weren't actually electrical faults. We engaged some very clever people who made a living out of explosives, and we were able to fairly well model the onset of an arc fault using moderate explosives, and that's how we managed our pressure rise versus time. But we can see the red line and then the black line, very steep initial rise, and then once the vent has opened, in the red case it drops fairly quickly back to a low pressure of around 2 kPa. In the 20 kA area we see a little bit of resonance in there. We haven't done detailed mathematics to understand that, but we understand that would just be some resonance in the enclosure, so that is, if you like, the air rushing in and out of through the port. But nonetheless, we see from a very steep initial rise, the pressure drops quickly. The energy in an arc is proportional to I squared times time. And the I in this case is the prospective fault current. It's It's not your load current. So don't confuse the two. Most engineers are listening on this call will understand that the fault current can be way different. Now, most electrical engineering managers in the mining area, in particular, want very high fault currents for direct online starting their big motors. So on the plus side, you can DOL a large motor, but of course on the other side, your prospective fault current is very high, and if you do have an arc fault, then you've got an even bigger problem. And a little tip there for the EEMs that if you want to start big motors, have a think about soft starters or variable speed drives. It's a much safer way to go about it. The other thing of interest is that low voltage plant is generally more hazardous than high voltage plant for arc faults. Firstly, the currents tend to be higher, and it's not unusual to find switchboards up to 70 kA at 415 volts. And we remember that the arc energy is essentially proportional to the square of the current, not necessarily the voltage. Breaking these high currents is harder, more expensive and invariably slower than at a higher voltage. And the personnel can generally be less respectful of a low voltage installation. If you tell somebody it's high voltage, they'll take half a step back. If you tell them it's low voltage, there's somewhat of a tendency to shrug their shoulders and say it might be okay, which of course we cannot condone. So arc faults, thankfully, are generally low likelihood events, but they do have a high consequence. And in managing arc faults, we need to think about our appetite for risk. I would argue that the risk we might take of an arc fault in an underground mine, which is a confined space with people in it, should be different to our appetite for risk of an arc fault in a remote location on the surface. Now, of course, the legislation talks about as low as is reasonably practical, but it's always difficult to try and quantify what as low as reasonably practical means. So there's old mate squatting beside a bit of electrical gear in a confined space. If we're contemplating what does it mean to have an uncontrolled arc fault, think about him squatting beside it, thinking all is safe, but actually being put in danger. So the hierarchy of controls. Well, the hierarchy of controls, from my reading, is embedded in a tedious document called the Work Health and Safety Regulation 2017. My apologies to any regulators who might be online for whom this is a critical document. But this is the OH&S regulation. It is not the mines version of the same. But in here, if we go and have a look at clause 36, it actually talks about the hierarchy of control measures. And it starts off saying that if it is not reasonably practical to eliminate the risk, then you must then follow clause 3 here that says, as far as is reasonably practical, you must substitute for the hazard, you must isolate the hazard, or implement engineering controls. Critically then it says if the risk then remains, the duty holder must minimise the risk as far as is reasonably practical by implementing administrative controls. Then, and only then, do you look to minimise the remaining risk by provision of PPE. So these people who jump up and say we've spent a hell of a lot of money on some PPE for these people, thinking they have undertaken their obligations under the regulation, I fear will be misled. Of course, that's the picture that we most often see. Elimination, substitution, engineering controls, admin controls, and PPE down the bottom. So what might that look like in the context of arc faults? Well, to eliminate an arc fault, we could, for example, use insulation. And we'll come back to each of these examples in a moment. Ultra-fast earthing switches and earth fault limiting are arguably substitution of one type of fault for another. Engineering controls that we can introduce include maintenance, local electrical protection, introducing fault impedances, managing the enclosure strength and venting. They all happen after the fault, but are controls that we put in place to try and mitigate the consequence. Under administrative controls, reams of paper will exist, but can I suggest it is something as simple as where to stand or not stand. And of course, PPE at the end, I don't propose to cover that here. We should really be focused on the upper levels of the hierarchy of controls, and I'd like to talk a little bit more about those options there. So factors affecting arc faults, the likelihood of an arc fault is, I think, governed to some extent by the insulation that we have, barriers we can put in place between phases, and the maintenance regime. Whereas the consequence is managed by, as we said, the ultrafast earthing switch, source impedance, electrical protection, enclosure strength, personal access. So here's an arbitrary electrical enclosure. And the thing I want to draw your attention to there are the exposed copper bus bars. So it might, I'm sure it does, meet with the appropriate clearances that are required for the voltage it's designed to operate at. But one can imagine that the vulnerability of such a layout to shorting between phases is arguably way too easy. By contrast, if we put some insulation on the bus bars, and unfortunately it's not a great photo, it's not well lit, but you can see the raycam there has been fitted to all of the exposed copper. And I understand that while that increases the cost of construction, it doesn't increase the cost of construction by nearly as much as one would expect if it's put in at the time of assembly. And I would argue that insulating the bus bars is one of the most effective ways to mitigate the likelihood of an arc fault. Quite frankly, if everything is insulated, then the likelihood of an arc fault should diminish to something which is reasonably practical. There's another image there, again where great effort has been put to maintain insulation across all of the exposed copper. Physical barriers. I've got a picky there on the right-hand side. We've got red, white and blue phases, and hopefully a little red circle there appears. It's difficult to pick up on this picture, but there's a physical barrier there between the phases. And what that is designed to do is to, I guess, increase the physical distance between the exposed copper such that the likelihood of a fault between those two phases is diminished. In this case, that barrier is an insulating barrier. Of course, there is an alternate approach where you can have a conducting barrier. Clearly, you need to rework all of your clearances around that. But if that barrier then is earthed, then the likelihood of a phase-to-phase fault goes way down compared to a phase-to-earth fault. Of course, if you have a phase-to-earth fault in an earth fault limited network, things are starting to become more manageable. So, an earth fault limited network, we've got a picky here. It's a general layout of a mining electrical system. So we have three phases that go to a mobile machine, and we also have a conducted earth, which comes back here through the neutral earthing resistor before it returns. So if we get a fault out of here, a fault to earth, then hopefully the current flows around there and it is being limited by the NER. If, however, we get a fault between phases, then that fault current does not go back through the NER, and hence a phase-to-phase fault in an IT system is not limited by the NER. And so the NER only helps us out where it is a fault to earth, not a phase-to-phase. And so that encourages us to try and design our equipment such that the first fault is to earth. And it's generally considered that around 90 to 95% of faults are to earth in the first instance. And of course, that's why we run the earth fault limited networks, and that's why we have a pretty good safety record in that environment. The ultra-fast earthing switch. The What we do here is to sense the onset of an arc fault and introduce a short circuit to earth. So these devices, they're proprietary devices. They're generally quite expensive, tens of thousands of dollars a time. It could tell a little story about a team of testing engineers who wondered if they worked, and so exercised them, and yes, they do in fact work. Then had to order some more, much to the chagrin of the project manager. But they tend to respond in something like 4 milliseconds, so very, very quick, and they change what arguably would have been a phase-to-phase fault through air. By shorting those phases to ground, we then have a sustained phase to earth fault, but of course that is much more manageable than the plasma that we're getting from an arcing fault. Maintenance. That's a lovely picky I found. Coal dust. It tends to cover everything in near a coal mine. Of course, there are other applications where surfaces get contaminated as well. Salt air is a classic where the moist salt can also be conductive. And when we have this compromise of the insulating surfaces, then all of our original calculations have gone out the window. Interestingly, in the case of coal dust, it adds an additional hazard in that the coal dust itself is combustible. And if we go back to the work of Ken Byers, they looked at a case where they did a number of experiments. So the key here is the distance D is between the electrodes where they induce the fault. We've got RMS current along the horizontal axis and the enclosure pressure up the vertical axis. On the left-hand side is a clean enclosure, and on the right-hand side is an enclosure that has been compromised with coal dust. The red line, red horizontal line, is at 11 atmospheres of pressure, and we can see on the right-hand side, for the same currents, for the same electrode distances, there is a lot higher pressure in the case where coal dust is present, quite simply because coal dust ignites and adds to the energy of the fault. And so the difference between a well-maintained enclosure and a poorly maintained enclosure with dust can result in a significant pressure rise inside the enclosure. Electrical protection. It's a fairly obvious one. Equally obvious is that it only protects downstream. So if we build ourselves an enclosure, we put some fuses in the front end where the incoming supply comes from, then everything downstream of those fuses will arguably be protected, but there is still a risk of an arcing fault at the front end of those fuses. So we can have some passive fuses. These are simple, fast-acting HRCs. They generally sense the overcurrent. We need to be a little bit careful with using fuses. There's a number of instances where fuses have been put in to protect electrical equipment but end up in a fire where we have a high impedance fault, which sits there drawing current through the high impedance fuse, because it goes into a semi-high impedance state. Then we have current flowing through high impedance. It gets hot, it catches fire, and the hazard there is the fire rather than electrical fault. So we need to be a little bit careful in using passive fuses in these applications. We can, of course, use active circuit breakers. These can be operated or sensed using overcurrent or light or heat or sound. Generally moderate operating times, but of course the available range may not suit the prospective fault currents in some applications. We can get significantly high fault currents, as we discussed before, and trying to find an active circuit breaker can be non-trivial in some instances. And we noted earlier that the arc energy is proportional to the square of the current. So of course, if we don't need a high fault current for our direct online starts, then we can arguably introduce some impedance into the circuit, and that reduces the fault current. It's not often done in electrical installations, but it just does underscore the sensitivity to current of the energy delivered in a fault. Also increasing the operating voltage. So if we have a constant power that we're trying to achieve, if the voltage goes up, then of course the current goes down. The arc energy is proportional to the square of the current, so there ends up less energy in the arc and fault in a higher voltage installation than in an equivalently powered low voltage installation. The upstream electrical protection. So an arc will continue until the circuit is interrupted. So the detection of an arc fault or overcurrent is something of the order of 50 to 100 milliseconds. Invariably, there are one or two or more intermediate relays of 20 to 50 milliseconds each. And then the operating time of the upstream circuit breaker, somewhere 120 to 250 milliseconds. So if we start to add those together, we can get getting close to 300, 400, 500 milliseconds of sustained arc. And as we saw earlier, the pressure rise in an enclosure is linearly proportional to the time of the duration of the fault. So sometimes people make the mistake of saying, oh, we can detect a fault within 50 milliseconds or 100 milliseconds. Well, that's only half the story. Detecting the fault is not sufficient to clear the fault. Obviously, you have to operate the breaker. So the longer delay, more energy delivered, more heat dissipated, and increased pressure rise. The other problem with upstream protection, of course, is that you have to communicate with it. And if there is a communications fault, then maybe your upstream protection doesn't work. A fairly catastrophic situation. But we also find that fault currents can be too low, or the tripping time is too slow to work effectively. Enclosure strength. Here we will talk initially about sheet metal enclosures, so what we generally call IP enclosures. So these come in many different shapes and sizes. They have different compartment sizes, different materials, different fastenings, penetrations and locking devices. So it's very difficult to come up with a single rule which allows you to generate a solution in managing pressure rise in these enclosures. We want to make sure that the enclosure is able to withstand the pressure rise for a given fault current, a given fault duration, and the enclosure construction. So arc vents, in essence, are the crumple zone of an electrical enclosure. In the same way that a modern car is designed to bend in case of an accident, then an arc vent is designed as the crumple zone of the enclosure. So that is where it will fail, and hoping that the rest of the enclosure stays intact. And there's an image there of an arc chute where an arc fault inside is venting through that chute there. Hopefully that's above head height. I don't have a scale on there. There's another image there of a simple panel, which is another type of arc vent you can have. So in the case of the orange one, that is IP rated. So you can maintain your IP rating on the enclosure, but that vent is designed to open. But of course, we've talked about what happens when one of those vents goes off and you get this flames and the molten metal spewing forth. So I would suggest that venting really only works when you've got an open space. I really can't condone its use in confined spaces, in surface installations where there aren't too many people around. I think a very effective solution. It's not a universal panacea. Picture here on the right-hand side. If it looks distorted, it's because the enclosure is distorted. Yes, that centre strut has been bent. The door is a little bit bent. There was an arc fault inside that and blew the doors open. That image there is of an arc vent which was fitted to that very enclosure around the other side, not in view. And that is the photo of the arc vent after the doors had blown open. And so in this case, it shows it was relatively poorly matched between the strength of the enclosure, or in this case the doors, and the vent itself. And whilst we don't propose to lecture at length on designing arc vents, it is not as simple as selecting a particular static pressure, say 10 kPa, 15 kPa, because these things must work very, very quickly. And so it is a dynamic system design, not a static system design. And I've come across a number of instances where people revert only to static pressures. But of course, as we said, the pressure rise is proportional to time. And so these vents must open very, very quickly. So I've got another video here, which is actually the same one we saw right at the start. And in this case here, we're going to, hopefully it'll be in slow motion. But if I can run it from here, what we see is some illumination behind the orange panel, and that is the onset of the arc itself. And so if you let the video now run a little further, we get to the point where the vent itself becomes overstressed and starts to open. And we can see there that it is actually cracked across the diagonal by design. There's a clock up the top here, and if we just have a look at the 755 milliseconds, that is when the vent has started to open. And as we run the video, you will see that the vent peels open, somewhat akin to a flower in its petals. You see both diagonals have opened now. We're at 759 milliseconds, so that is 4 milliseconds later. And at about 72 milliseconds, we can see that these panels are now fully opened. So that is about 7 milliseconds going from fully ingress protected to being fully open. And so when I talked about that previous example and having potentially been designed on static pressures, this is I guess a motivation for doing your design using a dynamic system where the inertia of the vent itself is a critical parameter. AS/NZS 4871 is, I guess, one of the better known electrical mining standards, and it does mention arc blast protection in there. Consideration shall be made for prevention of arc blast injury. This shall include handles, explosion vents, integrity guarding windows, etc. It's also mentioned under the enclosure requirements. The design of all enclosures shall consider, don't you love that in standards, you shall consider, excuse me, operator safety by means of vents located in a position to direct arc products away from the operator. So 4871 is actually the standard for portable, well, mobile and relocatable electrical equipment, be that underground or on the surface. So once again, I would say if you're on the surface, it's quite okay to direct the arc products away from the operator. If you are putting that underground, I suggest you need to think about where those arc products go as soon as they exit the enclosure. So getting back to these experiments we did, this is a switch room, high voltage switch room. We have a door on the right-hand side. We'll come to that in the next video, but that is where the personnel access the room. This is an access into the high voltage area, so normally it's not accessible. The orange panels are arc vents. And this is a test, I think, of around 16 Ka simulated. I love that because it's fun. But what we find is that both of the arc vents opened during the pressure rise there, vented the products in the enclosure and avoided damaging the door. So one of the very early shots in this presentation showed a door hanging off by half a hinge. That's what happens when you don't have vents. In this case, the vents have opened, released the pressure, and the rest of the structure is intact. This is the same setup now, but looking at the point of view where an operator might be. So we didn't have an operator in there. If you look closely, there's an operator hiding over here because you can't be too careful. But we did set up a camera inside. We also set up a number of different pressure transducers. But if we run that one, you might not have seen much happening there, and that's a good thing, because had you been an operator standing in there, our measurements indicate it was quite survivable, even though there was something catastrophic happening in the bulkhead or behind the bulkhead on the other side. And so that's an example of designing, trying to make it safe for the people, recognising that outside of that, there could be hazards elsewhere. Confined spaces, we stick high power electrical equipment in confined spaces, and there's old mate poking his head around. One can only imagine what would happen if we vented an arc bolt in that environment. So as I've said, confined spaces, they do present a hazard in managing arc bolts, and I really do think that more effort should be put into preventing arc bolts rather than trying to manage arc bolts in confined spaces. There's old mate again, keep him in mind. Typical fault currents, we talked about the significance of the fault currents. We did a little bit of homework to normalise around 1990 levels. So the work that Ken Byers did at SIMTARS in 1990 is 100% here. And if you look from 1990, 2000, 2010, 2017, we can see that the typical fault currents are around twice what they were back in 1990. The machine powers are, again, just something indicative: shearer, base conveyor, continuous miner, pumps, crusher units. Normalised to 1990, we can see we're up to 4 times the power here, 3 times the power. Interestingly, our electrical infrastructure has not changed much while the power has increased. So what about flame-proof enclosures? To date, we've talked about the standard IP enclosure. A flame-proof enclosure is not explosion-proof. A number of people think of a flame-proof enclosure as explosion-proof. They are certainly not. They are designed only to withstand the ignition of a volume of methane. They are not designed to withstand an arcing fault. So again, this work is taken from Ken Byers in 1990. Test number 211 had a spark ignition test in 9.8% methane and gave a pressure rise of 480 kPa inside the enclosure. And that's what a flame-proof enclosure is designed to withstand. When we put an arc fault in there, 3.3 kV, 11 Ka, 248 milliseconds, with no methane, test number 176, we got a pressure rise of 690 kPa. So you can see that if a flame-proof enclosure had withstood a methane ignition, it might not withstand an arc bolt. Just for a laugh, they did a combined test and had 9.8% methane and a 10 Ka arcing fault, and we actually get a higher pressure rise again. There was some interesting work on this flame-proof back in the early 2000s. There was a review of the work that had been done at SIMTARS, and it was pointed out at that time that because of the increase in currents and powers, that flame-proof enclosures could not be reliably expected to withstand an arcing fault with the sort of electrical equipment we were putting in. I think that was in around 2004. There was a significant paper written. But of course, now we're in 2020, the powers have gone up even more. And if there is ever a face-to-face fault inside a flame-proof enclosure, a failure of that enclosure becomes very, very catastrophic. Arc blast PPE. There is a standard which discusses that, and I don't propose to discuss it anymore. In the hierarchy of controls, expecting someone to work in a spacesuit, I don't think is the best we should be doing for our people. Finally, arc faults in cables and couplers. If one reads the literature from mine safety, there are a number of instances where there are arcing flashes from cables where people have driven over them or pulled them down off the roof or something or other. And of course, the same hazards are there. You've got radiation burns potentially. You've got blinding from the flash, electric shock. We have potentially ignition of explosive atmospheres and combustible materials. But significantly, there's no pressure rise. Because the cable generally isn't inside an enclosure, there is no pressure rise. So in that sense, they are slightly less hazardous than arc faults in enclosures. OEM claims, I won't bore you by reading through all of the words here in the document, but in essence, the standards make provision for manufacturers to test their performance of electrical equipment in the case of arc faults and to publish those. And I do remember seeing a video of one stage where it was reportedly a 50 kA fault sustained for 2 seconds. And I watched the video and I could not believe what was in front of my eyes. And I was told that it was done in accordance with AS 3439. And I said, good-o, and went away and read it. And basically AS 3439 allows you to test downstream of any electrical protection. And so from what I can gather, this manufacturer had put in some fuses, had put in an arc fault, downstream of the fuses. Of course, the fuses blew very quickly. And so they then continued to film for 2 seconds and said, there you go, 50 kA for 2 seconds. So please do read the literature that you're being offered to justify the equipment you're looking at. The concept of arc fault containment. Excuse my French, but I think that's bollocks. It is way too difficult to try and contain an arc fault. At best, we can manage it, we can try and prevent it, we can try and minimise the consequences, but I don't think I've seen anybody successfully contain an arc fault. Finally, to wrap it up, a couple of minutes overtime, this one came across our desks on the 12th of June, just a week or so ago. This is from New South Wales Mine Safety. I've got the full email there just for transparency. But if you zoom in on that photo, this was reported to be an arc fault in a piece of electrical equipment. And if we zoom in again, we find in this case, it's not a fault to earth or a phase-to-phase fault, but a single conductor has open circuited. I don't know how that happened, and I certainly won't speculate, but it just goes to show that when you think you've got your head around this stuff, there's always something cropping up to keep you honest. So I'll leave it there for the moment. Happy to field any questions that may come along. Thank you for your time and for listening.